In the last couple of videos, I introduced arrays and talked about array indexing. Now I'll talk about performing mathematical operations using arrays. This means that we can finally start exercising some of MATLAB's real power. Until now, we've mostly just been using MATLAB as a fairly sophisticated hand calculator. Now we can start doing some serious number crunching. As I mentioned in a previous video, MATLAB has a wide variety of arithmetic operators. There are, of course, the usual plus and minus operators which perform addition and subtraction. The rest of the operators come in two flavors, a dotted version and an undotted version. So multiplication can be done either with an asterisk or with an asterisk with a dot in front of it. There are four division operators, either a forward or a backward slash, with or without a dot. Exponentiation is done with a caret symbol, either with or without a dot. In this video, I'll talk only about the dotted operators and the addition and subtraction operators. We'll save discussion of the undotted operators until later. In short, the dotted operators and the plus-minus signs perform what are called array operations or element-by-element operations. As I said, the dotted operators perform array operations. This simply means that the operations are performed between corresponding elements of the arrays being operated on. This implies that the arrays being operated on, the operands, have to be the same size. Also, the output array will be the same size as the two operand arrays. Let's look at a few examples to illustrate how these operators work. We'll do a few using slides and then do a couple of demos using MATLAB. First, let's look at multiplying two arrays using dot times. The result is simply the multiplication of the corresponding elements of the two arrays. So the element in the first row and the first column is the product of 1 and 5. First row, second column is the product of 2 and 6. Second row, first column is 3 times 7, and so on. Dividing two arrays using dot slash is pretty much the same idea. The element in the first row and first column is 1 divided by 5. This element is 2 divided by 6. Down here is 3 divided by 7. And the final value is 4 divided by 8. The last example before doing some MATLAB demos is exponentiation. The idea is still the same as both of the previous examples. The element in the first array is raised to the power given by the corresponding element in the second array. So this element is 1 squared, or 1. This element is 2 to the 4th, or 16, and so on. There is an exception to the rule about operand sizes being the same. If one of the operands is a scalar, the scalar operates on every element in the array. The output array is the same size as the array operand. For example, if I multiply 2 times this array, the result is each element of the array multiplied by 2. 2 times 5 is 10, 2 times 6 is 12, and so on. Let's do a few examples of the dotted operators. First, I'll set up a couple of arrays to work with. I'll create an array A equals, open square bracket, 1 space 2 space 3, a semicolon, 4 space 5 space 6. So this array has 2 rows and 3 columns, and a second array, B equals, open square bracket, 0 space 2 space 1, semicolon, 4 space 0 space 3, close square brackets. B also has 2 rows and 3 columns. We can use dot times to multiply these two together. If we do that, we get 0, 4, 3, the second row is 16, 0, 18. Each element is the product of the corresponding elements in the operands. However, if I create another array, C equals, square bracket, -2, space 1, semicolon, 0, space 3, which gives us a 2 by 2 array, we can't multiply that by either of our previous arrays. The sizes don't match. For example, if I type C dot times A, I get an error. Now let's use dot slash to divide the two arrays. Type b dot slash a. Each element in the result is the element in B divided by the corresponding element in A. Notice that the numerator is on what I like to think of as the uphill side of the slash. Now let's use dot backslash to divide B by A. The syntax is now A dot backslash B. B is still the numerator and it's still on the uphill side of the slash, so we get the same result. If we multiply an array by a scalar, the scalar multiplies every element in the array. For example, 3 dot times A multiplies each element in A by 3 and gives us an array back that's the same size as the array A. Likewise, if we divide by a scalar, every element in the array gets operated on. A dot slash 2 divides every element in A by 2. Addition and subtraction using one scalar operation works similarly. For example, I can add 3 to every element in the array A by typing 3 plus A. As you'd expect, to square every element in the array A, we just type A dot caret 2. Since the operators have rules as to what size arrays they'll operate on, it's really important to be able to keep track of the sizes of the arrays you're working with. MATLAB provides a variety of commands to tell you how big your arrays are. Length returns the number of elements in the largest dimension of an array. This is particularly useful for one-dimensional arrays where length returns the number of elements in the array. The size command returns the number of rows and columns in that order in a two-dimensional array. Finally, if you just want to know the total number of elements in an array, the numl command will return that information. Now I'll incorporate arrays in an example I've already done with scalars. It's the beam deflection example of the second and third videos of Chapter 4. Now, however, we're going to calculate the deflection of the beam for a variety of x values. Here's the problem statement again. The beam is rigidly supported at the left end and the load's evenly distributed along the length of the beam. These are the physical parameters of the beam, and this is the equation governing the beam displacement, y, as a function of the distance from the fixed end of the beam, x. I'm going to modify the script file I created in Chapter 4 to allow me to put in an array of different x values where the displacement will be calculated. In this equation, W, E, I, and L are all scalars, so they aren't much of a concern. X, however, is now an array. That means when we square x here and here, we need to square the values in x on an element-by-element basis. So we need to use a dot caret operator here and here. In this term, we're multiplying a scalar, 4 times L, by an array, x. So this term is an array that's the same size as x. The term 6 times L squared is just a scalar. When we do these additions and subtractions, the term within the parentheses is an array that's the same size as the x array. This term is also a scalar times an array that's the same size as x, so this array will also be the same size as x. This array and this array need to be multiplied on a point-by-point basis because the location of x in this term needs to correspond to the x location in this term. I need to use a dot times multiplier here. In summary, I need to use a dot caret here and here and a dot times here. The other multiplication, division, or exponentiation operators are done on scalars. It doesn't really matter if we use dotted or undotted operators for those. They do the same thing with scalar operands. To start out, I'll create a new folder named Chapter 5 inside my MATLAB Demos folder inside the TIM folder. Just so I didn't get in a rut, I'll create this folder using Windows Explorer instead of MATLAB. So go to the C drive. In the TIM folder, I'll activate the MATLAB Demos folder, create a new folder in there named Chapter 5. Now I'll copy my script file from the second video of Chapter 4 into this folder and rename it as BEAM DEFL underscore array and use that as my starting point for this problem. Now I'll set this folder as my working folder in MATLAB. I'll type cd space for change directory, starting at the C root directory, C:\tim /MATLAB demos /chapter 5. To edit the file, I'll type edit space BEAM DEFL underscore array. Now I need to change the multiplication and exponentiation operators to dotted operators. Now I can define the x vector as an array. Let's evaluate the deflection at values of 2, 7, and 12 inches. Now save the file. I'll run the file by typing the file name BEAM DEFL underscore array at the command prompt and press enter. I get 3 deflections corresponding to the 3 x values. The first value in the y array corresponds to the deflection at the location specified in the first value of the x array. The second element in y corresponds to the location in the second element in x, and so on. I can easily modify my file to calculate the displacement for a lot of x values. I can use colon notation to create an array of x values, starting at 0, having increments of 0.0, 1, and ending at L. Save this, run it from the command window. These are the deflections for all of those x values. Consider the function y of t is equal to 3 times e to the minus t over 2 times the cosine of 4 times t. I'll evaluate this function over the range of time t equals 0 to 10 seconds at intervals of 0.01 seconds. Before we continue, I'll make a quick comment about MATLAB's built-in functions when they're applied to arrays. For the most part, mathematical functions will return an array which is the same size as the array that's sent to it. Each element of the output array will be the result of applying the function to the corresponding element in the input array. Here are a few things to keep track of. We'll have a vector of times with 1001 points in it. So the cosine of 4 times t will also be a vector with 1001 points, as will e to the minus t over 2. This isn't a problem with MATLAB. If we send a vector to the functions that implement cosines and exponentials, we'll get a vector back that's the same size as the input argument. We need to multiply these two vectors together, point by point, so we have to use a dot times between the two of these. The scalar multiplications and divisions, 3 times this, t over 2, and 4 times t, are going to be operations between a scalar and an array. Now, it doesn't matter whether we use dotted or undotted operators in these locations. They both behave the same under those circumstances. First, let's set up the vector containing the times. I'll use colon notation to do this since we're given the spacing we want between the time points. I'll name the variable t, give it a starting value of 0, an increment of 0.01, and a final value of 10. Now I'll implement the equation. I'll name my variable y and set it equal to 3 times exp of minus t slash 2. exp is MATLAB's function to evaluate exponentials. Now we use dot times to multiply this vector times cosine of 4 times t. COS, as you might guess, is MATLAB's cosine function. I'll follow this with a semicolon, since I don't particularly want to see all these variables scroll by, and press Enter. Now my values are in the workspace. If I actually do want to see them, I can type the variable name and press Enter. This isn't terribly informative though. There's really too much information here to be useful. If I'm interested in something specific, like for example the minimum or maximum value of the function, I can use MATLAB's min and max functions to return these. So to return the minimum value of y, type min of y. The maximum value is returned by max of y. But these numbers don't really give me much of a feeling for what the overall function's doing. Probably the best way to get a feeling for the overall function is to plot it. Luckily, that's really easy in MATLAB. Just type the command plot and put the x and y data in that order as arguments to the function. So type plot of t, comma, y. So the time data is on the horizontal axis and the y data is on the vertical axis. Pretty cool and easy, right? I'll talk more about plotting in our next video. I'm now done introducing the basics of arrays in MATLAB. You know how to create arrays, access particular elements of arrays or ranges of elements in an array, and use MATLAB's dotted operators and built-in functions to perform array mathematics. Arrays are great in that they allow you to work with a whole bunch of numbers all at once. They do have a drawback though. Humans aren't good at extracting information from a collection of numbers. We're highly visual animals, and it's easier for us to extract information from plots and graphs than from tables of numbers. At the end of this video, we created a plot. MATLAB has outstanding plotting capabilities with lots of options and abilities to customize plots. In the next couple of videos, I'll introduce some of the most useful and basic plotting capabilities. Okay.